Assalamualaikum and a very good afternoon. So today I will cover up in terms of the chapters under the mobile robotic coursework, which is the planning and navigation. So this is an outline of my lecture, consists of 5 main topics: introduction to local and global navigation, the definition, and then I will cover 3 main algorithms for the local path planners, which are artificial potential field, vector field histogram, and Nearness diagram. So mobile robotic, when we say about the mobile robotics, the robot shall able to reach its destination, which is the target area, and then at the same time it shall follow the generated trajectories. When reaching the destination, it can explore the new item in that things and then map that area. And then the most important thing is that during navigating to the target, it able to avoid any collision. Means that if know the location of every obstacles and then find the free space, that able to avoid any collision. So basically the mobile robot can be divided into 2 main categories. The first one is the holonomic, and then the second one is the non-holonomic. By definition, holonomic means that the robot can actually move straight away towards the target, let's say in the X direction, Y direction. For the non-holonomics, it need to reposition itself in order to reach the destination. So for instance, for this particular case, for the holonomic case, if this is the robot and then this is the parking lot, the holonomic just need to move straight away in order to reach the destination. However, for the non-holonomics, in order to reach the parking lot, it should move in any arbitrary direction before it can reach the final destination. The second definition is based on the definition of local and global navigation. So basically, for the local navigation means that the robot aim is to avoid any collision during navigation. So because of that, it will relying on its onboard sensors. And then usually for the local navigation, the target location will be after the obstacle, straight away after the obstacle. So in contrast with the local navigation, the global navigation map everything prior starting the navigation task. So means that it requires a map information. Let's say we have the map, we have the robot, and then pinpoint the final location, and then the robot should generate the path towards that particular goal location. However, in practice, usually the novel navigation will be actually integrated with the local navigation because of during navigation there is some new obstacle was introduced. So because of that, the robot need reroute in order to avoid that particular obstacles, and then later on finding back what is actually the final location of the destination. So for this lecture, I will more focusing on the local navigation, which I will cover up in terms of the 3 main algorithm. The first one is the artificial potential field. Second one is the vector field histogram, is actually some improvement from the artificial potential field. And then finally the Nearness diagram, which is introduced some sort of the improvement based on the likeness of the vector field histogram algorithm. So artificial potential field was introduced by Osama Khatib around 1968. So basically for this particular algorithm, the objective is that the manipulator will move in the field of force. So the field of force means that consists of 2. The first one is the attractive, and then the second one is the repulsive. So attractive is by definition is the goal location, and then repulsive is actually the force that was generated by the obstacle. So potential field can be actually defined as the array of vectors that representing the space. So vector usually consists of the 2 main items, which is the magnitude and the direction. So the vector will be known as the force, So this is actually the generally what is actually the rectangle will look like in a real application. So basically the series of vectors can be in terms of uniform formation, perpendicular formation. So attraction means that move towards the object. Repulsion means that move out from the objects. And then tangential is something like the force that is circling the object. So by definition, so for the artificial potential field consists of the two parts, the attractive and then the repulsive. So attractive is actually the one generated from the goal location. So it can be calculated by using this equation, means that x goal and y goal is the goal location, and then x and y is actually the current location. So from this thing we can actually generate the attractive vector, also known as the attractive force. So in difference for the repulsive, so the repulsive can actually be calculated. Let's say this is actually based on this particular equation. Usually if we use let's say laser rangefinder, we can get the angle information. So what we need to do is that we need to define the magnitude. So basically for this magnitude is actually d minus d over d. So the capital letter of D means that this is actually the maximum capability of the sensors. Let's say if we use the first class laser rangefinder, the maximum capability is around 5 meters. So V magnitude was calculated based on the, let's say, 5 meter minus what is actually the current distance of the obstacles over D. So from this we will actually generate series of the repulsive force based on the obstacle current location. So for the potential field, it will actually straightaway sum up the information regarding the attractive force and then the repulsive force. So you can imagine this is actually the goal location which generate the attractive force. So this is actually the obstacle that is generate the repulsive force. So the summation of everything will generate this uniform pattern move towards the goal. So based on this thing, actually we can generate what is actually the optimal path. So in a simple way, let's say for instance this is the vector of attractive, this is the vector of repulsive. So by sum up both vectors, we can actually obtain this type of vector. So this is actually the path that will be generated based on the summation of these two forces. So in other cases, for this particular case, if we have the attractive and repulsive in a same magnitude with a different direction, the sum will be null. So for this particular case means that we won't generate any movement for this particular condition. So this is actually general equation for the potential fields. So means that we generate in terms of the xy, we represent that thing in terms of the vectors. So the vectors can actually be defined as some sort of the differential equation. So for real implementation, actually we don't have to calculate the potential field for every location from the image. What we need to do is that we just need to rely on the sensor information. Let's say you have the laser rangefinder with 250 degrees of field of view. So you just need to get the reading from the 250 degrees information. So you don't have to compute everything for the entire field. So finally the motor vectors. So the motor vectors actually will be generated. Usually we just rely on information with respect to the angle. So which angle or which direction the robot should move based on the summation of the attractive and the repulsive force. So for the attraction and the avoidance, so actually what we have is that we have the goal, so it means that generate the attractive force, and then the second thing we have the obstacles that actually surround with the repulsive force. So for the ideal result, actually the robot will move towards the goal and then at the same time avoid the obstacles. So in order to cater with the dynamic obstacles, dynamic obstacle means that the obstacle that actually move during the robot moving. So for this particular condition, the system need to update the information regarding the new attractive and repulsive force in order to generate the final path. So one of the bottlenecks of the artificial potential field is that the local minimum problem. I will show you actually what is actually this problem. And then the second thing is the unstable oscillation, because we actually relying on the summation of the vectors. So if let's say in some situation that the summation of the vector is quite wrong, or actually the generated path is actually oscillate, so for this particular case means that the robot will be oscillate even though it shall move towards the straight line. So this is actually one of the issues of the local minimum. So means that let's say this is the obstacle location and then this is the goal location. So as we know, for the potential field, so the obstacle will generate the repulsive force, and then this is actually the goal will generate the attractive force. So one of the biggest issue is that for this particular case, when you have the vector here and then by assumption that there is symmetry, so all the vector generated here will be cancelled out by the vector generated here, and then for this particular case you have the attractive force in here. So the robot will try to move towards the goal for this particular case, because of the robot cannot detect what is actually in the left or in the right side, even though we have some sort of the obstacle. In a simple way, the local minimum problem is that the robot will stuck in the U-shaped obstacles. Either it is in a uniform, it is a symmetry or not, but something like in the U case obstacle, because for this particular case, the repulsive force generated will be cancel out each other, and actually because of it cancel out the effect, so robot did not notice any obstacle in the left or the right side. So this is one of the issues of the artificial potential field. So next we move on to the second part of the algorithm, which is known as the vector field histogram. So basically for the vector field histogram, the algorithm works in a different way in comparison with the artificial potential field. So what actually the vector field histogram do is that first it will construct the local occupancy grid map. Local occupancy grid map means that for each of the particular location, what is actually the probability that we have the obstacles. So this is actually true for a condition in which we have the sonar sensor. However, if we use the laser rangefinder, means that the probability of the occupancy for each of the grid map is actually always 1. So if we use laser, every location of the obstacle will have the probability of 1. So this is the first step. The next step is that we need to develop build the polar histogram of obstacles. So the local map is actually in the 2D formation. However, the polar histogram is actually in 1D information. I will show you later on how we are able to do this conversion. And then later on, based on the generated or based on the constructed polar histogram, so the algorithm will select what is actually the steering angle in order to avoid collision in one particular condition, and then at the same time it try to move towards the target. So as I mentioned earlier, so in the case where the robot will be used for the local navigations, the target location will be put just after the obstacle location. So this is actually in a simple way how the vector field histogram works. So this is your robot with some sort of the sensor readings. This is the laser rangefinder. So this is actually the obstacle. So we have, this is actually the 2D maps of the robot, or we also call this thing as the top field view of the robot. So based on this 2D reading, so the next part for the vector field histogram is to generate the polar histogram. So polar histogram is actually was generated based on the sensor reading. So means that let's say for this particular case, for this robot actually we have the reading of sensors from negative 180 degrees until 180 degrees, and then the center of this thing is always the direction that the robot will move. This is actually the center location of the robot. So first we have the map, and then second we have the polar histogram. So the next part is that we need to select the threshold. So when we select the threshold, any value of the polar density that is lower than threshold will be 0. So for this particular case, we don't have any value here, and then we don't have any value here. So it means that we just have this thing will be remain. So in order to determine the steering angles, so G is actually based on the A, B and C is actually the constant value. We can set this thing depending on the heuristic method. So A times with the target direction plus B times the wheel orientation, and then C times the previous direction. So this is actually the cost function that will be used in order to generate what is actually the optimal direction in order to let the robot move to the next stage. So once we have the polar obstacle density, so the robot will select any location that is safe. For this particular case, for the green area is actually the safe area, while the red sector is actually the unsafe area. So I will make the things clear for you in the next slide. Okay, so this is actually some sort of the example on how we able to use the vector field histogram in order to let the robot navigate safely. So for this particular case, this is actually the view of the robot. So you see we detect some sort of the obstacle in this hallway. So this is actually the top view of this particular area. So this is one obstacle, and then actually we have some sort of the obstacle in here. So this is actually the polar histogram, in which it will generate some sort of the polar density of the vector field histogram. So for this particular case, the red means that this is actually the dangerous obstacle that the robot should avoid. Green means that this is the obstacle that is quite near to the robot. So we just put it in the caution list. Yellow is actually any obstacle that is below the threshold. So yellow means that the obstacle is still far from the robot, and then it can be ignored during navigation. White is actually the free space. So usually based on the width of the free space, we will actually generate the steering angle. So this is actually for this particular case the optimal steering angle. So based on this condition, if we use the vector field histogram to navigate in the hallway, or let's say next to the wall, we can actually generate quite smooth movement. So in contrast with the artificial potential field, because of for the potential field, let's say this is the targeted movement, and then this is actually the repulsive force. So there is some tendency that the robot will move to the left, even though it should move straight, and then it's actually quite safe in order to move straight. So this is some sort of the visualization on how we able to use the vector field histogram in real time. So I will show you the video. So this is the same thing, the robot view. So it detects some obstacles here, and then this is actually the real-time information regarding the polar obstacle density. So for this particular case, the steering angle will actually be generated based on the yellow area. So you can see from here, and then this is actually the red, means that it's dangerous. So let me show you how the thing will work in practice. So for this particular case, we try to navigate the wheelchairs to move cross the obstacles safely, and then move back to the initial location. So the system, we use the vector field histogram in order to generate the safe motion of the robot, and then later on we try to avoid this obstacle, and then reorientate the wheelchairs to the safe direction, and then when it's safe, it will reorientate towards the final destination. Okay, so that is in terms of the second algorithm, which is the vector field histogram. Now we'll move on to the final algorithm, which is the Nearness diagram. So basically, for the Nearness diagram, the implementation of the algorithm is almost the same with a vector field histogram. But the additional part is that more detailed analysis of the valley in order to generate the final angle. So first thing first is that the same with the vector field histogram. For the Nearness diagram, based on the sensor reading, we will generate some sort of the same information from the vector field histogram, which is the polar histogram. So however, for the Nearness diagram, we call it as the RND. RND known as the robotic nearness diagram information. So RND is almost the same with the polar obstacle density, only how the Nearness diagram use the RND is quite different in comparison to the vector field histogram. For the Nearness diagram, it used the divide and conquer strategies, so in which it will classify the RND, robot Nearness diagram, into 5 different situations. So this is the situation A, B, C, D, E. So for the A situation, the first situation, so this is actually the safe direction of the robot, and then it will detect some sort of the obstacle. For this particular case, we have the goal location after the obstacles, and then for this particular case, we have only one free space. For the second case, means that the same thing, we call it as the low safety one. This is the low safety 2. For the low safety 2, we have the goal location after the obstacles. For this particular case, we have 2 valley in order to go to the goal direction. So A and B is known as the low safety case. So C is the high safety case. C, D, and E is the high safety case. For the C condition, we have actually the goal location in the white valley, in the free space white valley. For the second case of the high safety, means that we have very wide region for this particular obstacle. And then the last section of the last situation of the Nearness diagram means that for this particular case, we have the obstacle location after the obstacle. We have the goal location after the obstacle. However, for this particular case, we have narrow region. So this is actually all the condition that was considered in the Nearness diagram in order to generate the next path. So based on these 5 conditions, Nearness diagram propose 5 action in order to encounter this particular situation. So for the first condition, you remember, this is actually the goal location. So for this particular case, we just have one free space. So what the robot should do is that the robot should move away from the closest obstacles and then move towards the gap. So it means that for this particular case, it just move away from the obstacle and then towards the gap, should move here. For the second case, means that for the low safety 2, so what the robot should do is that this is the first space, free space. This is the second free space. So the robot should move in the between of the safest gap, and then it will select which area. It should be no problem which area that the robot will choose, either in the left area or the right area. So depending on what is actually the direction it was selected. The third case means that the goal is actually in the white area. So for this particular case, it's quite easy. The robot just moves straight away to the destination. So the fourth case means that we have a free walking area, and then we have the obstacle location here. So what the robot should do is that it will move alongside the obstacle. Just move in here in order to reach the goal location. You don't have to we don't have to put that thing in the center, in the middle, or whatever. Just move near to the obstacles and then straight away towards the goal. And then for the final location, so because of this is actually very narrow gap, so what the robot should do is that first it need to move itself in the central area. So let's say this is the gap. The robot need to move in the center area first before it can avoid the obstacles and then later on move towards the goal. So this is actually 5 condition of the Nearness diagram and how it should considered in navigation in order to ensure that the robot able to reach its destination and then at the same time can avoid the obstacle. So this is a sample of the implementation of the robot. Some simulation of this thing. This is actually the robot Nearness diagram, how it was manipulated in the navigation. So I have some sort of the simulation in the online website. You need to watch that thing, and then later on you need to answer all the question that was listed in the website to fulfill your FOC requirement. So that's all. Thank you very much.